Hello, in this video we'll continue with Boolean algebra properties. So here we're going to talk about theorem of the uniqueness of complements. For any x in the Boolean algebra, if an element x1 exists such that x plus x1 equal 1 and x dot x1 equal 0, then x1 must be the complement. Why is that? If you think about it as set, you have A union not A, you get universal set S, or maybe U for universal set. It's equal to everything. So A union with what gives me everything, except if we have the complement of A. And similarly, A intersect with what give me an empty set. A is common with what set that will give me an empty set? That must be not A. So if this case, x1 must be the negation. Let's see some examples here. Let B is a set that has 0 and 1, A and not A. And let the plus and a dot be binary operation on this set B. The unary operation negation is defined as follow. So if you have 0, you negate that, you get 1. 1 you negate it, it's 0. A negates is not A. A not is just A, double negation. Then suppose you know that this Boolean algebra B plus that, this is the set of Boolean algebra. Making use of the properties that must hold in the Boolean algebra, let's fill in this table. So take a minute and think about it. We know that x plus the 0 is x. If you forgot, you set A union empty set is A. And x plus 1 is 1. If you want to think about it with respect to set, if I have set A union with the universal set, I put it as universal set with everything. That means I'm going to get everything because I have a union. It's an OR. You have everything. I mean you have 1. So let's apply this to this table here. So 0 plus 0, that means you have the identity property. 0, 1, A, not A. And plus 1, you get 1 everywhere. And then A plus 0, when you add a 0, again, you get A, you get 1, A, and 1. A naught plus 0 is A naught. A naught plus 1 is 1. Plus 1 is 1. A naught plus A is 1, because A or not A, that will give you a universal set, which is 1, which is S or 1. Not A or not A, that is just not A. Similarly here, we have a dot. Same table, but dot. So let's see what we know. X dot 0 is 0, the identity. And then x dot 1 is x. The identity is x dot 1 is x. And the complement. Okay, so now if you do 0 dot 0, you get 0. That 0 is always 0. And 1 dot 0, 0. 1 dot 1 is 1. 1 dot A is A. 1 dot A naught is A naught. And A dot 0, 0. A dot 1 is A. A dot A is A. A dot A naught is 0. An empty set, right? A naught dot 0 is 0. A naught dot 1 is not A naught. A naught dot A is 0. And A naught dot A is A naught. This is just to practice these properties here. Okay, let's see this example here. We need to prove that x plus x naught y is the same as x plus y. Algebraically, that means using those properties of Boolean algebra. Okay, so we start with the left hand side, and I hope you have those flashcards next to you. And let's see, what can we do? So I'm going to just rewrite it so we understand better, similar to the properties. All what I did here, I'm rewriting it. And now I could use the distribution property, which is 3a, and look at the flashcard and tell me what is that. So it's going to be x plus x naught dot x plus y. We use 3a distribution property. And now, what is x dot x naught? This is 1 and x plus y. What I use is 5a. Next, you know 1 dot anything is the same thing. That's the identity we just reviewed. So x plus y, which is 4b. So we went from one side, we get to the other. Let's understand it with the truth table. What we're trying to prove is that, as I highlight here in yellow, is that x plus x naught y is the same as x plus y for different inputs of x and y. So x and y are inputs, are wires, for example, and these wires will have either an on or off switch. For example, we could have 1, 1, both ons, or 1, 0, and 0, 1, and 0, 0. This is the same at truth table we did before at the beginning, when you have true, 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 false, false, true, false, false. But here, we use 1 and 0s because of the switches. It could be 1 or 0 when we talk about network, the logic network or the circuits. So 1 and or 1, this is 1, this is 1 and 1. 0, remember this is an OR here. You could think about it true, false, but that's an OR. Second, I'm going to negate x naught, which I have 0, 0, 1, 1. And then this is a dot in between, it's an AND, which gives me 0, 0, 1, 0. And now, if you look at the last two columns, how you get to this x plus x naught y, it's going to be 1, 1, 1, 0. So as you see, for the same input, we get the same output. So they are the same. Again, later on, this is in chapter 8.2, next section of the book, we're going to deal with an OR gate. We call them gates. And here is the wire. Maybe it could be X and Y. And we design OR gate looking like this. Different books would write it. So when these two wires cross this gate, they get X or Y output. So if you have 1, 1, the output is 1. If you have 1, 0, the output is 1. So on and off, you get O and so on. And then you have the AND gate. And the AND gates, as you're going to see in this book, is represented somehow like this. I'm writing AND, so I differentiate between the two. So we'll be dealing with these two. So what does it mean, one side and the other side? So X plus Y, I already have it right here. So which is better, basically, to draw this or to draw this one here, which is, here is the X. And then we're going to take the X and we're going to negate it. And here is the negation gate. Okay, and then we take the wire Y. And then between them is an AND gate. And then between the X and this X naught Y, it will go through an OR gate, which is this symbol here, plus. And then finally, it will give you that expression at the end. This is basically X plus X naught Y. So which is better, as I said earlier, to design this or to design this one? Because for the same input XY, 0, 1, 1, 0, 1, 1, 0, 0, you get the same output. So, except that this one, I need 1, 2, 3 gates, but this one I have only one. So as an electrical engineer, for example, or computer scientist, you would better design a logic circuit that has less gates because it will cost less to build. I hope this gives you an overview of why we're doing this, why we need to prove things, why we need to go from one expression to the other. Because at the end, we need to find out what is the best design. Because they are the same, except one will cost more than the other. I hope this is helpful.